So good afternoon, everyone. I'm going to be talking about database-driven machine learning. So let's just have a show of hands. How many of you use databases? Okay, that's pretty good. How many of you are developers? Cool. DBAs? Okay. How many of you data scientists? Okay, cool. How many of you use Python? Excellent. The language R? Okay, very good. And SQL? Okay, you're in the right place. So I work at ROracle in this middle building in database development. I write C code for a living in the database kernel. So in the 18.1 version of the database, I wrote about 30,000 lines of C code in the kernel to do stuff. That's half of my job. The other half of my job is I'm a cloud product manager, and I'm very focused on machine learning because we're using a lot of that technology for the autonomous database service. So, first of all, hands up, anyone a lawyer here? Okay, so I'm legally required to say this. I'm making some future statements and I don't want to influence your purchasing. So, we've got 43 minutes, I've got about 50 slides and some live demos. So I encourage questions. I'm going to be asking you questions. You can ask me questions as well, but I do want to make sure we get through the material. I'm very happy to spend a lot of time answering questions at the end. So the journey today is a little bit of an introduction to machine learning. I don't assume you know anything about it. If you know lots about it, that's great. If you know a lot about it, you might disagree with some of the stuff I say. I certainly have opinions on this. We're going to be looking at using the machine learning algorithms within the database via SQL and PL/SQL, looking at how we can use machine learning against data in an Oracle database outside the database using Python and R. And we're also looking at some of the techniques we're using in machine learning for the autonomous database. So there's going to be a bit of theory. We're going to look at some useful concepts. We're going to go down to the code level, do some demos, and I've got lots of opinions, so just take it all with a grain of salt. Now, I'm going to try and use examples of machine learning. So one example is feedback. It's called reinforcement learning. Great questions or good answers get feedback. And there's I think, a really important theoretical concept which you may or may not know, and there's 20 quid for the person who answers it correctly without Googling it. Okay, so back when I did computer science many, many years ago, I studied AI amongst other things, and I thought that's cool, but it's also kind of useless because most of it didn't really work in a practical way. So, are you guys familiar with that sort of technology? Okay, hands up if you think it's the best thing since sliced bread. Okay, hands up if you think it's pure evil in 1984. Excellent. So, what we were talking about there, I've got a lot of high-level stuff. This is sort of the marketing fluff, and then we're going to dig down into the code. But natural language processing and voice recognition, it's out there. You can buy this stuff. You know, I live in the US, autonomous vehicles, Teslas, they're everywhere. You can't get away from them. So the point is, it's out there. So, any of you recognize this stuff? So this Tesla had a bit of a navigation issue in Belgium. This Google machine, you know, had a bit of a head-on crash. And unfortunately, there was a fatality in Arizona recently. So just hands up. Are self-driving cars ready? Would you ride in one? Okay, so this to me was an example of machine learning. This is called a bias sample. Google's done millions of hours and they had one crash. So a big thing in machine learning is your data. If you're looking at good data, that's great. If you're looking at very biased samples, you're going to get biased results. So, what is machine learning? One of the challenges of machine learning is if you ask 10 experts, be it theoretical practitioners, you're going to get 10 different answers. So it's a science, but it's an evolving science. So lots of different definitions. I like the original one from 1959. Basically, things get better by looking at data without being explicitly programmed. And this last quote, it's about money. Most of the money in machine learning is about targeted ads. So we've talked briefly about voice recognition, natural language processing, vision, just in those first examples. But most of where machine learning is in different areas. In theory, it can be used for pretty much anything, but the most well understood areas are these. I'm not going to read them all off, but the point is there's well-defined areas that has been shown to be useful today, and they have names like classification, like regression, associations. So the point is, it's a very broad field, but there's specific, well-understood techniques. But more importantly, where can you make money doing this? So, I mean, I have a bias. Back when I was at college, I cared a lot about the theory. I did the stuff. What I care about now is making money or saving money. There's lots of different algorithms, there's lots of different ways of doing it. I don't really care. I care about, for my job, how I can solve problems, how I can make money, and how I can save money. So here's just some examples. You know, you guys heard of Google and Facebook over here? So I come from the US, so just trying to get a perspective. But I mean, they make billions of dollars in targeted ads. That's where they make their money. So they're using a lot of machine learning algorithms to figure out who you are, what you've done, what you're interested in, and try and put up ads which they think are relevant to you with the hope that you might click on it, which is how they get their money. A lot of machine learning I don't actually like. It doesn't fit with my outlook on life. Some things that I find somewhat useful are Amazon. If I purchase something, it might recommend something else that I might like. Likewise, Netflix. If I'm watching a movie, I might be able to suggest another one. So that's a technique called associations. Anyone here heard of Cambridge Analytica? Okay, I come from the US, so please don't talk to me about that. Okay, so if you've heard a little bit about machine learning, people will say there's two types. There's supervised and unsupervised. But actually it's more complicated than that. There's also semi-supervised learning and reinforcement learning. So the point is, there's no perfect categories and simple way of describing this. It's complicated, it's messy. So given these different techniques, you can use types of machine learning. Like for supervised learning, you can have classifications. Likewise for reinforcement or semi-supervised. So these different techniques at a high level might use the same sorts of things under the covers. So another way of looking at this, you know, many years ago I did lots of statistics, theoretical and applied. And all of those techniques are technically machine learning. So if you're doing regression, you know, the slope of a chart, y equals mx plus c, or linear regression, looking at those factors, like those are all technically machine learning. Limited in what they can do, but they're still machine learning. So a lot of what people talk about nowadays are neural networks. That is but one technology out of many that you can use. There's not just one technology that fits everything. Another example here, classification. Solves many different problems, and yet there's many different algorithms that you can apply for classification. Regression is completely different from classification, likewise clustering, and yet all three can use neural networks. So it's not a whole lot of distinct things. There's a lot of overlap. So, you know, I'm just coming up to the end of the theoretical part, which hopefully gives you an introduction to some of the stuff I'm going to be doing. So the point is, machine learning, it's about algorithms, it's about data. You can apply it in many different places. It's not machine specific, it's not language specific. So for instance, I did some research recently, and Python followed by R were the two languages with the most number of libraries out there. So this is changing every day, but that's sort of the trend. So this is the £20 question. What is that algorithm? Any takers? Yes, sir.
Something that works out Bayesian probability.
Excellent answer, but not correct. Any other takers? Yep.
A computer program.
Another very good answer, but not correct. Yes, sir.
Steps that need to be taken in order to achieve a goal, achieve a result.
True. This is a very specific theorem. I'm after a very specific answer here. Any more takers? Like if you're Googling this, it's not going to count. Any other answers? Okay. This is the no free lunch theorem. Sounds weird. It's true. Google it. So what this says is there's no algorithm that's better than all other algorithms for any data or domain. So this is really important. I mean, it may seem trivial, but it's important because it has implications. So there's no best algorithm. Given a specific domain, given specific data, and specific parameters and hyperparameters, there will tend to be one algorithm that's better. So if you see someone who's into machine learning saying, I'm using language X with library Y, it's perfect, it does everything, they're lying. Or worse, they don't understand. So there's a lot of theory behind this. Machine learning is very domain specific. It's very data specific. Okay? So if you learn nothing else, it's that. Keep an open mind. So the point is, in machine learning, there's a ton of math, there's a ton of theory. Yes, sir?
Wouldn't it be easier just to design a dopamine receptor on a chip and give it so that the equivalent of biological imperatives and then forget about all the math?
That's an excellent answer. So yes, that would be great. It's kind of difficult to do that, but I like where you're going. So the point being, even though with machine learning there's a lot of theory and a lot of math behind it, like when I did neural nets many, many years ago, we had to write it in C or C++. Nowadays, there's libraries that do it all for you. But the point is, you need to understand what problem you're trying to solve, what algorithm you should use, and what parameters and hyperparameters you need to make that algorithm work. That's why it's hard. So as Grady Booch used to say, a fool with a tool is still a fool. I do this for a living, I consider myself a fool. It's hard because there's so many options. So it's really easy to get caught up in buzzwords and algorithms and doing stuff. But unless you're actually solving real problems, I don't think it's useful. So I would claim that to succeed in machine learning, you need a bunch of things. You need a really well-defined problem. If you don't know what you're trying to do, you're wasting your time. You need lots of data, specifically clean data and normalized data. So if you've got, if you're Facebook, you've got millions of machines with lots of data based on points and clicks on compute nodes and an HDFS file system. You probably want to use Hadoop for that. But they actually spend most of their time cleaning up that data, normalizing it to make it useful. If you do machine learning in a database that's got a schema with types, most of that problem's already solved for you because the type is a number, the type is a date, the type is a string. We've already enforced that for you. Biggest problem you've got to deal with is missing data or null data. So once you've got this clean data, say it's a table, you've got lots of columns, you've got to figure out for the problem you're trying to solve, what are the most important attributes? Is it column A? Is it column D and F? Or is it some mathematical relationship between those? Next, you've got to figure out which algorithm and parameters and hyperparameters that you need. Also, a lot of machine learning involves training. That takes time. Never underestimate how long that takes. And ultimately, the result of all this is you need to have an actionable insight, which means it needs to do something useful. You have more, you have an answer, there's something you can do about it. If you want to make money out of this, you've got to be able to take that solution, whatever it is, and productize it. Just because it works on your laptop or on your cloud doesn't mean it's ready to go production. It's got to be effective, efficient, and robust. And guess what? You're not done. By the time you've done all that, the world has changed. So you've got to tweak things. So it's a process. It's an ongoing process. Now, some of the demos I'm going to be going through are neural networks. There's lots of buzzwords about neural nets and deep learning. So I'm just going to cover that very briefly. So the point is, there's many different algorithms out there. Neural nets are but one. And by definition, they can't solve everything. So, in 60 seconds or less, neural networks have been around for a long time. Back in the 90s, when I was doing computer science, it was very hot. It was the thing to do. Very recently, they've become hot again because with increased computing power, and especially GPUs, you can do a lot of things now that you couldn't do back then. So fundamentally, you're mimicking what a biological neuron does. So one way of thinking is you've got neurons which can connect and do something useful. So at a high level, you have inputs and you have an output. It's a bit more complicated than that. You can have many inputs to represent pretty much anything, but you want to get the right answer. So to make neural networks work, you've got to have known inputs and known answers. And then you can train the network to do what you want, be it to do image recognition, voice recognition, drive a car, do clustering, do regression, a bunch of different things. So the point being, if you have inputs and one or more layers in the middle, you can get outputs. And the training is automatically figuring out the weights for those different perceptrons. Okay, so you either understood that or you didn't. The point being, you can end up with more complicated things. This has got 2 layers of hidden networks and 5 nodes. You can have an unlimited number of internal networks, hidden layers and many, many nodes. There's no limit. But there is actually a limit. It's called processing power. It takes time to train these things. So that was 60 seconds or less. So now, that was the theory. Now I'm going to look at the application. Just doing a time check here. Okay, so I'm going to be talking about machine learning that's built into the Oracle database. I'm going to be talking mainly about how you do that in SQL and PL SQL. There's also Enterprise R that sits on top of that. It literally reuses it. So I'm just going to focus on the SQL. I'm going to talk about R in a different part of my talk. So this is a blatant marketing slide. The important thing is the headings in red are the different types of problems that can be solved using built-in machine learning algorithms in the Oracle database, specifically in advanced analytics. So, you can do classification, and there's many different algorithms you can use to solve classification. Likewise, regression. I'm not going to read it all out. The point is, there's a bunch of stuff in the Oracle database to do this stuff. Now, the other really important thing about machine learning, big data, is move the algorithm to the data, not the data to the algorithm. Your algorithm might be a few kilobytes. Your data could be terabytes or petabytes. So it's far quicker to move the algorithm to where the data is. If your critical data is in the Oracle database, it makes sense to me to process it in the database, quite frankly, because it's faster, it's more efficient, it's cheaper. If your data is on a compute farm, it's probably better to have the algorithm running on the compute farm, something sitting on top of Hadoop. If you've got a bit of both, then you have choices. So those APIs are there. A lot of the Oracle applications already use this technology in a bunch of different ways. Once again, that's marketing. I want to get to the code. But before I get to the code, I just want to look at the model or the approach that Oracle uses for machine learning in the database. Your data normally lives in tables. So one of your inputs is going to be the table or view that you care about, because that's where your data is. There's probably a column that you care about that you want to process. You've got to figure out what type of problems you want to solve and what type of algorithm you want to use. We use that by calling a stored procedure in PL SQL. And you want to specify your parameters or hyperparameters, and there can be a huge list of those. So we represent those as rows in a table. So you create a table, add some rows, given known values. So that's how you set it up. When you execute that stored procedure, it's going to run the algorithm for you. If it's a small amount of data and a simple algorithm, it can be pretty quick. If it's got billions of rows, it could take a lot longer. So it depends how long it's going to take to run. Once you've finished that, you can use SQL to analyze it. So this is the high-level concept, and then I'm going to show you a couple of examples of how you do that in practice. So imagine you're an insurance company with policies. And just imagine some people make fraudulent claims. If you're an insurance company, you want to try and minimise paying out on those fraudulent claims because that's going to affect your profit. So just imagine you have a table called claims. And imagine you have a column called policy number in that table. So that's your table, that's your data. We're going to create a table called claim set. It's an arbitrary name. It could be called, any string. Call it Brexit, whatever you want to call it. So the point is, you're going to add rows to define what that thing does. So in this case, it's going to use a support vector machine, which is a very efficient way of doing classification. We're now going to call our stored procedure. We're going to call it an arbitrary name, claim model. We're telling it you're going to solve a classification problem. We're telling it the name of your table. We're telling it the column of interest. And there's a bunch of other parameters which you can basically default. So when you execute that against your claims table, we can then use SQL, over here, we can see there's policies and percentages of fraud ranked from highest to lowest. That's the outcome. The way we got that SQL is we were doing a select from your claims table, and we're calling a SQL function prediction probability. So that's obviously not a standard piece of SQL, that's Oracle's enhancement. But that SQL function is looking at the data mining function, data mining model that you created. We've got a where clause, and we're using the ranking analytics function to give the top 5. So the point is, machine learning's hard. What we've done here with using data mining from advanced analytics is we've taken your data from your table, you've chosen the algorithm you want, which is association. We've created that model, we've executed it, and we're getting the result in SQL. So if you write that in some other language using some other library, that's a lot of work. So this is a way that you can process it in your database with your data. So that's the first example. Any questions on that?
So 12, what are those articles?
Great question. Since 10G, there's been a lot of features, and each feature, they add more. So for instance, in this next one, in 18.1, the Oracle database, they've added neural networks. So in different versions, they have more and more algorithms. Okay, so here's another example. We're following the same pattern. but instead of doing support vector machines, we're using neural networks. So we're creating a table, we're adding parameters. So because it's a neural network, we're telling it's a neural network, we're saying how many nodes per layer, we're telling it how many hidden layers there are, I'm telling it how many iterations I want to use for the learning. So that's defining what's going to happen. We're creating, giving it a name, I'm telling it its classification. Instead of using a table, this time I'm going to use a view against the ID column. When I run that stored procedure, it's going to take, the time to take that is going to be proportional to the amount of data you've got in that table. So this particular problem is looking at affinity cards and the probability that you'll use them. Sorry, that's loyalty cards. Think a Tesco card. What's the probability that you're going to use that loyalty card? So I've done loyalty card, loyalty systems with many different companies. Companies love them because even though you're saving money, you're likely to keep using that company because you're saving money. If that company's getting your money, even at a reduced rate, that's more money that they're going to get if you went to a competitor. So it's kind of a win-win, but a lot of companies spend a lot of money on this because it's useful to them. So this is about predicting the probability of using that loyalty card. So we ran it, we're querying it, we're looking at the prediction probability, and we got some answers. And if we do a different query here, we can see how accurate it is. Gasp! It's only 75% accurate. Here's another thing to learn about machine learning. It's not perfect. You'll figure it all out, you'll run it, and you'll get a result. And 9 times out of 10, you're going to be unhappy with that result because it wasn't as accurate as you wanted. So that means you've got to tweak it. Am I using the right parameters? Am I using the right algorithm? So you keep tweaking it. So it's a science, but there's a lot of art. Because if you got the perfect answer each time, we'd all be done. It's not that simple. Yes, sir?
That transposes you already know the answer to the question before you ask the question.
Do you want a crunchy bar, a Twix, or a Twix? Is health and safety here? Catch. Excellent. There's different types of machine learning. This type of machine learning, you have to know what the answer is. So you've got known inputs and known answers, and you train it. There's other types that use unsupervised where you don't have to. Another type's reinforcement learning. I just gave you reinforcement by giving something you want. So there's different types. So I'm not saying this is a good type. I'm saying for the type of problem, which in this case is association, this is a useful algorithm. The cost is you have to train it. Excellent question.
We never get 100% as humans. We don't use the word probability. Yes, I'll come with probability of 75%.
Correct. What do you want? Sorry, I can't hear. Either?
The problem is in our day-to-day lives, we are not looking at the uncertainty and the things that we do, the decisions we make, and yet we're asking a heck of a lot of machines, aren't we?
I totally agree. This is only useful to a certain set of problems, and you have a model. So, given data, given a problem, you create a model. If it doesn't work out to be useful, the smart person will say, what have I done wrong? What can I change? The naive person said, my model's perfect, the data must be wrong. Okay, do you want to catch? Good catch. So from the questions, you're understanding what I'm talking about. It's hard. It's not perfect. People who tell you otherwise are trying to sell you something. Okay, so I very briefly looked at two algorithms that you can use within the Oracle database to solve some very specific problems. What I'm now going to look at is, instead of using the built-in functions to the Oracle database, how you can use external languages to do machine learning for the data in the Oracle database. It's like, if you're doing machine learning against a compute node, don't use this stuff because it's not relevant. But if your business critical data that you want to solve your problem for is in your Oracle database, then this is what's relevant. So I'm going to be looking at how you do some machine learning in R and how you do it with Python. So a bunch of you used R. Some of you may or may not use RStudio. I like it, makes it simpler. So the point is, it's a scripting language which is, very much designed for statistics, but it can also do other things like machine learning. Specifically, it's got interface for database drivers. Oracle created their own driver for that, so instead of using generic ODBC or JDBC, they wrote their own driver in OCI to make it go fast. And that driver is called ROracle. So, shameless product plug. I work in database development, but I use the ×10 scale-out database, which is a new shared nothing scale-out product, which we're going to launch next month. The point being, how you do things in the Oracle database is exactly how you do things in the ×10 in-memory database. So you can write the code once, deploy it both places. So under the covers, it just used 10S names to figure out how to connect things. So I'm going to start with a simple example and then a more complicated one. Hotspots is a way of visually representing complex information. Usually the darkest or brightest thing is the thing of interest. And you can apply that to many different problems. I'm looking at it as if you had a clustered database and there was a hotspot, that's probably an area that you want to look at, because if all those processing nodes are doing the same amount of information, you've probably got the best scalability. If some are doing too much, it's going to limit your scalability, or there might be a problem. So if you figure out where they are, it can help you. How could we do that using R? So people using R who know R, this is probably simple, but the point is use some libraries. So we're going to use the ROracle library, another library for some transformation, and we're going to use the D3 heat map library to render that. So we've got to connect. Let's use the Oracle driver, give it a username, password, and a database name. This code will work exactly the same for Oracle or my database ×10. So the result of that connection is you get a handle. That handle, if you can read that, you've got better eyesight than me. So we're going to do a database query. Given a handle, you run a SQL select statement. And we're going to pass that off to our heat object so that we can render it. So I'm sure you can't read that, but that big, long, complicated thing is actually a single SQL statement to get all the data of interest. Because that data is coming from many different tables, we're having to jump through a few hoops. We're using with, and we're using some unions, and some group by and another union. The point being, the whole thing is technically a single statement. It gives you a result set. So we've connected, we've run a query, and we've populated that result set into a heat object. And right down the bottom, we disconnected. So we connected, got the data, and disconnected. Because we got the data into an R object, we don't need the database anymore. So what we want to do is render it down the bottom here. But that library wants data in a certain format. It wants data in a matrix format and row column format. So we've got to do some transformations to get there. We've got to pivot the rows to the columns and get rid of some headings. But the point is, this is very typical. You got data in one format and your library wants it in another. So you've got to do some transformation. And that assumes your data is perfect to start off with. So it's a very typical sort of pattern. When you render it, it shows you the hotspots. So this clustered database just happens to be ×10 scale out. So in that node, looks like it's having some problems. So maybe a person, or maybe some machine learning code, can look at it to figure out what we could do. That wasn't really machine learning. That was visually showing you where the important thing is. It basically got a matrix of numbers, and based on an algorithm, the higher the numbers it coloured it to show it. But instead of showing it, we could take those highest numbers and say, those nodes have got a problem. Should we observe it a bit more and see if it fixes itself? If we think it's fundamentally got a problem, maybe we could reboot that node. Or if we think it's really bad, we could evict and replace that node. So whether you're displaying it or using it as an input to another algorithm, that very simple technique can be useful. So we've got a neural network in R. Now, neural networks are a theory. You can write them by hand. What most people do is they use libraries. Some libraries are really high level and they do a lot of stuff for you. Some are really low level, give you more power, but you've got to do more coding. So this is an example of a really simple, high level thing. So we've got some data, we're using a library. This library's got some existing data set. If you basically call that function, it's going to download some data off the network, and it's going to give you some data in a matrix format. It just happens to be about college admissions. I come from the US, my son's just going to college. It costs a lot of money. So figuring out, do you go public, do you go private, where do you go it? Financially, it's a big deal, and this is simulating that. So the point is, I'm not going to go through all the code, but the point is, with most machine learning, you're dealing with numbers. You can do it with ordinal types, but in most cases it's numbers. You've got to clean the data. Normally you've got to normalize it, so it's a number usually between 0 and 1, or negative 1 and 1. You've got to put it in a format. Also, when you're training, if you got a whatever the machine learning is, if you train it, supervised learning, you've got inputs and you've got outputs, and you train it. Do you know whether it worked? Why don't we run it against the test data? Is that a good idea? Why is it not a good idea? Exactly. So you have to have independent data. Normally the simplest way of doing that is you get data and you chop off part of it, say 20 or 30%, put it aside. You train it with your 70 or 80%. When you're happy, you then run it against the data that you haven't seen. If you get good results, all that means is for that data set, you're getting a good result. Was that data set representative of other data in the same problem? Maybe, maybe not. So if you run your machine learning algorithm against new data and it doesn't work, maybe your model wasn't good, or maybe the original data wasn't representative enough. That's not theory, that's just reality. These are things you need to deal with. So the point being, you split off your data, and then you call your neural network, and you get a prediction, and for the hell of it, with this library, you can render it. So you can see what the inputs were, what the nodes were, and what the weights were. That's useful for learning. It looks pretty, but it's not needed in production. But it's just for this purpose of this demo so you can see what it was doing under the covers. So that was an example of a really high-level neural net written in R. Yep.
Sorry, that example.
Yep.
Does the training happen on the machine which is hosting the R client or on database?
Excellent question. This particular, I cheated here. This particular one I stole off the internet. You download the data from a website and it runs it in R. But more specifically, if you had the data in an Oracle database, you would use the technique I used in the prior example. You would connect, you would query, you'd have it in a data object. Given the data object, then you do these transformations. If you had loaded the data from Oracle into the R object, by definition, all of that data is running in R. R has limited memory. So that's the thing. If you use the algorithms built into the Oracle database, you're not copying the rows from the table into memory and doing stuff. It's processing directly against those rows. An Oracle can have petabytes, zettabytes of information because it has buffer cache management. If you load the data from the database or from the file system into R, you're limited by the memory management of R. If you're running it on your laptop, you're screwed. If you're doing it on a big server, you can do more, but it's still going to be limited by the physical DRAM on that machine. Excellent question. Would you like a crunchy bar or some M&Ms? Okay, so did you understand what was going on there? If you load it from whatever the file system or your database into memory, that's how much data you can have. If you've got 16 gigabytes, you can't even have 16 gigabytes. You can have less than that. If you've got a really big machine with a terabyte of memory, it can be a bigger result set. If you're trying to process petabytes of information, it's not going to fit. If you use the Oracle database, it can load stuff in and process it as you go. So that's a very practical implication. You're going to be most of the time you're going to be limited by the physical memory of the system unless you've got a clever library. Yes, sir.
You only use the functions that Oracle has specifically built in the database, or do you use general RAM libraries but mounted into the Oracle R installation?
Okay, so if I understand the question, I think it was, can you only use the built-in functions or can you use external ones? If you're using the machine learning built into advanced analytics in the Oracle database, you basically got to use the machine learning algorithms that are built into the database. You can use arbitrary SQL, PL/SQL, and analytics on top of that. If what you're doing is very specialized and Oracle flat out doesn't support it, which is possible, then you might need to look at using, some external library, be it R, Python, or whatever your favorite language is. Does that answer your question? Okay. Yep.
So do I assume correctly that if we read data into R or into Python and process it there, it should be a little bit faster than processing it in the Oracle?
Great question.
Not necessarily.
Not necessarily. I mean, at the under the covers, all of this is calling C libraries, which go at about the same speed. If you're moving terabytes to a C library, it's going to be slow. If you're running a C library in the same address space as the data, it's going to be a lot faster. So the answer is it depends, but given equivalent environment, it tends to be about the same. So I'm just doing a time check. I am about 10 minutes behind, so I'm going to speed up. Great questions. So Python, same sort of deal. There's a Python driver. The guy who wrote the original Python driver now works for Oracle. So CX is the open source supported way of doing it against Oracle. Shameless plug, works the same with times 10. So you import the library, you connect giving a username and password, you create a cursor, you run some SQL, you pass in a bind variable, you can print some stuff out. So to connect, run SQL, get the data and disconnect, very simple pattern. Once you got that data out in an object in Python, you can then use Python machine learning libraries to do things. Make sense? Okay, second example, doing a neural net in Python. Many different libraries to do that. I'm looking at Tensorflow because it's a cool one to do. So Google open sourced this. Google basically calls it the machine assembly language or the C version of neural networks because it's incredibly low level. So all the other examples I showed fit in one page. From the TensorFlow website, the simple example took 8 pages. So it's things that you do in one step, in one function, in one library. In TensorFlow, there's lots of steps. So I'm just quickly showing it. You start off using the Python number library, which is very useful, TensorFlow library. You're setting up your model. I skipped the 8 other pages. You finally train it. They're doing it in batches, 20,000 iterations. You evaluate it. So you're getting the same result, but you have to do a lot of more lower level stuff. TensorFlow is really cool. If you've got a cloud of machines with GPU, it can process stuff efficiently in parallel, but you've got to take on the responsibility for owning the steps more yourself. So the final part of the talk. How long have I got? Okay. I'm now going to talk about what I really want to talk about, which is autonomous databases. So I'm the product manager for this, so I'm kind of responsible for what it does and how it does it. So there's a lot of things that an autonomous database does, provisioning, automatic patching, upgrade, backups, blah, blah, blah. What I want to talk about is self-tuning the database to make the SQL go faster. I don't think we're going to have time to go into the self-diagnostics. So, as I said before, I don't really care about the theory, I care about the results of machine learning. So, if you've got an OLTP database, I care about the actionable outcomes. What can you do about it? Who here tunes SQL? Who's good at tuning SQL? Okay, sir, do you have an algorithm, a way of doing this? Hold on, I think I recognise you. We have a rock star here, that's Gerald. How do you tune, Gerald? Yeah? Excellent, excellent answer. Anyone else? Yes, sir. Excellent answer. That's a way of doing it, and I like that way, because that's how I do it. Gerald's lazy, I mean smart. I do it the same way Gerald does it. 20 years ago, TK Prof, explain plan, weights. Gerald uses a technique to do it for you. I'm going to be talking about an equivalent technique instead of in the Oracle database in times 10. So the point being, ultimately with OLTP, if you can't change the schema and you can't change the SQL, you might be able to add or remove indexes. You might be able to update statistics, 5 minutes to go. There's a bunch of things you can do. More importantly, is this going to happen all the time, automatically? Or are you going to tell me, only advise me about it, or don't do anything because you don't trust it? Those are going to be your choices. Ultimately, how effective will this be and how efficient will it be? So I'm just going to quickly summarise a talk I went to a few weeks ago. A professor from Carnegie Mellon said, autonomous databases, we do those. We're excellent at them. He's got a bunch of postgrads doing it. And then he said, Oracle's doing it, but it's crap. I thought, that's interesting. We haven't told anybody how we do it. So what he fundamentally said was, Oracle's reacting. That's no good. You need to predict the future, because it takes a long time to do these things. If you predict the future, you've got more time to do them. I thought, that's interesting. So what they're doing is they look at SQL. They look at all of the SQL, not just the important bits. They look at all of the SQL. Because there's so much data, they can't process it in a timely manner. So they use machine learning techniques to get clusters. So from millions, they get into tens of thousands. They use another machine learning technique to drop that down to a few thousand. And then they use some association rules. Like, they're not using one algorithm, they're using many of them. It's all these hybrids, until they eventually end up with a recurrent neural network. And they make predictions. So given a cyclic workload, they can predict what's going to happen. And you can see here, sometimes they get it wrong. So these professors said Oracle's doing it wrong. I thought, game on. They make predictions once every hour. Why? Because all this processing is expensive. They say, don't just run your Oracle, Oracle database, MySQL, Postgres, whatever database. Run a cluster of GPUs machines, because that's the processing power they need to make these predictions. It takes them 25 days of training data to make a prediction of the future, but guess what? They still make it wrong. So it's expensive. Yep. So they're very focused on predicting the future, which they don't do very well, and it's expensive. And their actionable outcome is they create or drop indexes. I don't think that's very good. I think there's a better way. So, shameless plug. My database is an OLTP database, 144 million transactions per second. Okay, it's pretty fast. If you just do reads over 1.2 billion a second. How do you automatically tune that? Instead of using trivial SQL, I'll just quickly show you more complicated. This is TPCH, and that's hung, so just bear with me. We've got less than a minute here, so pressure's on. So what I'm trying to do here is log into the Oracle Cloud. All right. So the first time you run it, it takes time to speed up. What I'm doing here is I'm running some SQL against the TPCH schema, many millions of rows, I get answers. It's fairly fast. Run different queries, goes pretty fast, lots of joins. Life is good. But there's always that evil query which takes too long. In this case, we're joining many tables, we're doing order bys, bunch of analytics. It's taking longer than I want. I want to automatically tune the slow SQL. Not all SQL, just the slow SQL. So I'm going to train my database against that SQL. So I'm going to start capturing it. I'm going to run that SQL again. It's going to take a bit longer because I'm training it. So I'm using machine learning to figure out what their data is and how it might go faster. Okay, so the first time it took about 10 seconds, that took a bit longer, it was about 14 seconds because it was training it. Now I could train, a workload for an hour or whatever, it's however long you want. So I'm going to stop running it and, it gave me some recommendations, a bunch of indexes. So I'm going to cut and paste that. So what we're seeing here is just the advisement. Instead of advising, actually doing programmatically is not that hard. So I'm creating a bunch of indexes. There's many millions of rows there. I've created those indexes. Let's run that query again. So remember, it took about 10 or 11 seconds the first time. And it took about 5 seconds. So I don't know or care what the SQL was. If you identify what the hot SQL is and tune that, things get better. So what I'm saying is, don't try and predict the future, because it's hard. Anyone good at predicting the future? Okay, so you don't need to. How long have I got? I can't read that. Okay. We're done. So we look at the inputs, we look at the outputs, we evaluate it. If we can do that frequently, say every minute, we can have a self-tuning database. So just to summarize, machine learning is complex and it covers many areas. Does a lot of stuff from statistics. If your critical data is in your Oracle database, be lazy, be smart, use the functions built into the Oracle database. You can do it with other languages like R and Python. You've got to do more yourself. You're going to be limited by the memory in the machine, but it'll work. And we're working on self-tuning databases for the times 10 autonomous database service. So that's it, done. Any questions? Yes, sir. I believe so. So I think we're running out of time. I'm happy to answer more questions afterwards. Thank you for your time.